All right, so last time we were talking about vectors, and a vector is basically just kind of, it has a direction and it has a magnitude to it. We showed the clip of potentially ruining Despicable Me. Bad guy's name is Vector, and it's got direction and magnitude. So, and it kind of has a look like it's a coordinate. So it talks about a vector. We basically plot that point, and you plot that point and basically treat it like a coordinate. So now you have this horizontal part to it because that's your x. You got a vertical part to it, that's your y. And then the hypotenuse is the magnitude. So basically you're just doing Pythagorean theorem to figure out its magnitude. So that's, again, like if it's a physics thing, that might be the velocity that it's going in. And then there's a direction to it. The direction is this angle down here. Okay, so you can also use SOHCAHTOA to figure out the angle to it. Now, this doesn't ask for that specifically, but I believe one of them does. So that's kind of a quick refresher that nothing new is happening. The language might be different, but as far as the math that's happening on this, nothing new. You're doing Pythagorean theorem to figure out the magnitude. And then we did this, was our last one that we did, was it gave us that same point and it wanted to know the direction. And so we were looking for that angle right there. And so it wasn't asking for the magnitude, but it was asking for that angle. And so given that angle, we had the opposite and we had the adjacent. So that meant that we were doing tangent. So we set up tangent of the angle that we don't know equal the opposite over the adjacent. Over adjacent. And then since you're missing an angle value, that's the only time that we ever do that inverse on your calculator. And that spits out that angle. So about 37 degrees is the direction that that thing would be heading. Okay. So again, the terminology is different, but we're still doing SOHCAHTOA. We're still just kind of solve and find missing pieces of a triangle. And this was, and remember that when they do ask for the direction, it's always from that vector to the x-axis. It's never going to be out here. It's never going to be within here. We always draw our triangle to the x-axis, never to the y-axis. Okay. So you're going to see that's happening again in this world called polar coordinates. But you're going to see that everything we did here on these vectors are going to be exactly the same. But the way that we write it is more, rather than writing it as a coordinate where we're out 4 and then up 3, we're going to write it as an angle and a magnitude. That's all that polar coordinates are. So it's like a regular coordinate, but it just gives you different information. Okay. So, so a polar coordinate system is different, and it's definitely different than what you're used to. This rectangular coordinate system is what you've always known, right? X and Y axis kind of thing. Well, a polar coordinate system is circular. So to look at what it is let me share a screen here for a second. There's a graphing program online that's free and you can get an app on it. It's called Desmos. And it will show you, like, this is what you're used to. And so this is what you're familiar with and what you're used to. This grid is a polar coordinate. Now it looks crazy, but it is, let me do this, that all it's going to be is, rather than us having an X and a Y, we're going to have a magnitude. So we're going to have a distance out. So if the magnitude is 2, we would be out here. And then you have a degree on. So if it was 45 degrees, we would follow this circle of 2, and that's exactly where we would be. Okay, so if you write a coordinate on it, let's see if I can do this right. If I do 2, 45, maybe. Yeah, maybe not. I think it's still wanting me to plot. I've never tried to plot it on here actually before. So, but when we do this by hand, and you'll kind of see that we're going to draw some of this stuff. So if it says 2, we go out to 2, and then 45 degrees would be here. 60 degrees would be up here. So that we kind of follow that line. If it was 460, we would go 4 and then 60. So our point would be right there. Okay. So that's what polar coordinates look like. They still could give you a coordinate, but it's just a different way of describing a coordinate. So we're just talking about a bunch of circles and then so many degrees kind of up. All right. So let me go back to that. So here's kind of this example of it. And when we draw our angle, we always draw kind of from the positive x-axis, right, is what you're familiar with. And so we kind of start and we'll draw in that direction every single time. Okay, so if it said 30 degrees, we're going to go from here. We're not going to start out here. We're not going to start. It's always going to be kind of on the positive x-axis, and then we just start going in a counterclockwise fashion. That direction that you're going is exactly why, believe it or not, when we name quadrants, you know, we always kind of start in the upper right and then it goes to the upper left. That's 2, that's 3, and that's quadrant 4. It's because of trig, actually. It's because of us starting in this and heading in this direction when we draw our angles. And that numbering system is exactly because of the direction that we go when we do our trig stuff. So there was reason, you just never knew why. Like, why do we start in the upper right-hand corner? Why do we go to this quadrant? And then why do we go here? Why do we go here? It's because of how we draw our angles. So look at that. All right, so here's an example. So if you see this right here, that first value is the magnitude. Okay, so that is going to be a distance out. So that would be out 3. And then 45 degrees is that we would open up then 45 degrees. So that is your direction. Okay, so rather than it being an X and a Y, it's a distance out and then so many degrees. And that's what a polar coordinate looks like. All right, so it's still going to get you to a similar location, just a different way of describing it. Okay. All right, so let's kind of go through a couple of them. So that was, we went out 3 and then we rotated up 45. Okay, so it looks like this. So this is, and they use R because it's a radius of a circle. So that is your magnitude, this R. And then there's your angle, your direction that you're going. Okay. Now, again, there's all sorts of memorization thing that you need, but we're going to show you that you don't have to know any of this because it's going to be same stuff that we've already done. It's going to be actually very similar to this sort of stuff. Okay, so we're not creating anything new at all. Again, the language and kind of how we look at it's a little bit different, but as far as the math goes, we're going to be doing the exact same stuff. We're going to use SOHCAHTOA and we're going to use Pythagorean Theorem. Okay, so I'm not going to try to say, hey, look at all these new things. You don't need it. Okay. All right, so here's what they're going to ask for. They're going to say, all right, here is a regular coordinate. We're going to write it as a polar coordinate. Okay, so there's 2 pieces of information that we need. We're going to take this and convert it into a distance out, aka magnitude, aka Pythagorean theorem, hypotenuse thing, and we're going to need to figure out an angle. That's what our end goal is. All right. So I don't know about you, but I am way of a visual person when it comes to math, especially if I can draw a picture. I'm absolutely going to draw a picture. Just makes things easier for me. So I'm going to plot this point. All right. So we're 1, 2, 3, 1, 2, 3, 4. Okay. So that's the point. And what I want to know is if we were to have created a circle for this, how far out, what would the radius be of that circle, and what would this angle be? Those are the 2 pieces that we need to find. So like I said, we are not doing anything different. We are going to drop this down to make a triangle. We know that that distance out is 3. This distance up is 4, according to the coordinate. And we need to know hypotenuse, and we need to know this angle. Okay. So what can we use to find the radius, the hypotenuse? We know the 3 and the 4. How can we find the missing hypotenuse here?
A squared plus b squared equals c squared.
Exactly, Pythagorean theorem. So 3 squared plus 4 squared equals r squared. So we're looking at 9 plus 16 equals r squared. So 25 when you add those. And then we square root. So that r, which is also the magnitude, same concept, same idea, is 5. Okay, so that's our r value. That's that distance out. So if you were making a circle, you would have a radius of 5 on it right now. All right, and then using the 3 and the 4 again, what SOHCAHTOA piece could you use to figure out your angle? Right, that is your opposite.
Tangent.
Perfect. And this is your adjacent. So opposite and adjacent, so tangent. So tangent of theta is going to equal opposite over adjacent, 4 over 3. And then to actually figure out your angle, you're going to be doing the inverse tangent of that. And that's what we'll plug into the calculator. All right, now before you go too far on any of this, make sure that your mode, so you hit the mode button, make sure you're in degrees, not radians, otherwise it's going to screw everything up. So we are in degrees. So we're going to do inverse tangent of 4 divided by 3. And that is the angle. So that's the direction. So 53.1. So our coordinate is the distance out, which is 5. And then the angle up would be 53.1 degrees. Okay, so both plotting that point going out 3, up 4, or drawing a circle with a radius of 5 and kind of going up 53 degrees would put you in the exact same location. They both get you the same spot. Just different ways of looking at it. Okay. So, new point, same stuff. Make sure we're okay. So again, I'm very visual. I'm going to start by plotting the point. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 8. And we're going to draw a triangle. So we are out 5, up 8. We're looking for the hypotenuse, which is the radius, and this is our angle that we're looking for. Okay, so again, we're converting this into kind of a piece of a circle. So a radius and an angle. So a vector and the direction, or the magnitude, I'm sorry, magnitude and the direction. All the same stuff. Okay, so really, it's really the same process every time, because we are given the exact same, every time you're given a coordinate, you're always given an opposite and an adjacent. And then so every single time, if you want to figure out that distance up, you're doing Pythagorean theorem. And when you want to figure out the angle, you're always going to do tangent. Right? Because even though I'm about to find that value, I'd like to avoid using that one just in case I got it wrong. So if I always use the given pieces of information, I'll have a better chance of, like, I could still get the angle right, but the length wrong, just because I don't use the wrong value. Okay, so if we do the Pythagorean theorem, we got 5 squared plus 8 squared. It's going to equal r squared. So that's 25. 8 squared is 64. That's 89. square root. So if you square root, I don't know, it's not a perfect square. Square root of 9, we get 9.4. And then again, I'm going to try to avoid using this just in case. So if we're going to be finding this angle, we still have the opposite and adjacent, excuse me. Opposite adjacent, so that means we're going to have to use tangent again. And you're going to see that that's always what you use. So we got 8 over 5, opposite over adjacent. So to find an angle measurement, we're going to do the inverse of that. And I don't know, inverse tangent of 8 divided by 5. So we'll call that 58 degrees. Okay, so our coordinate to give us the exact same location as 5, 8 would be if we went out 9.4 and then we rotated up 58 degrees. That would give us the exact same location. Okay, is that okay? Nothing crazy new. Okay.
So far, so good.
So let's go the other direction. Okay, and again, yeah, there's formulas and whatever, but again, I don't want to create new stuff for it. I want to take what we are already familiar with and not tack on something new. Let's use what we already know. So this time is you're going the other direction. Here's your distance out. Here's your angle up. What coordinate would that thing look like then? That would get you the exact same location. Okay, so again, to me, it's all about, let's figure out how to draw a triangle and then we can use stuff that we already know. Okay, but we got to make sure we understand how to draw this one. So it's about a bunch of circles because this is your distance out, that's your radius, and then that's an angle. So if I draw this, I'm going to be out 1, 2. So it's like I have 2 circles basically is what I'm looking at. Okay, so I'm out 1, 2 and up 30 degrees. So where this crosses the circle, that's where I'm at. That's where that coordinate would be. So this distance is 2 and my angle is 30. I'm going to draw that bigger. Need more space. Okay, so I'm out 2 and up 30 degrees. So maybe somewhere right there. So if that's 30, this distance is 2. Okay, let me actually just draw that separate. Okay, I would be dropping down a chord. I would be dropping down right there to make a right triangle. So what I need to know is how far is the horizontal and how far is the vertical, because the horizontal is your X, the vertical is your Y. So this is your X, this is your Y. We know our angle is 30 and we know our hypotenuse is 2. Okay, so how do you find your X and your Y? So let's say we want to find X for no other reason than X is first in the alphabet. So we don't need anything, we don't want anything to do with Y, so we'll ignore that. So from this angle, what would X be called and what would 2 be called? So we can figure out which trig function to use. what would x be called compared to 30? The opposite, the adjacent, or the hypotenuse?
Did you say the opposite, adjacent, of hypotenuse? Wouldn't that be the
Well, which
opposite?
one of them? Would
Oh.
x be the opposite, the adjacent, or the hypotenuse?
Adjacent.
Perfect. So this is the adjacent.
And then y would be the opposite.
Good.
And then 2 would be the hypotenuse.
Good. Perfect. Okay, so if you're trying to find x, you have the adjacent and the hypotenuse of what you're dealing with. So which trig function is that going to be? Adjacent, hypotenuse.
Cosine.
Cosine, perfect. Yep, adjacent and hypotenuse. So we're doing cosine of 30 would equal adjacent, which we don't know, over the hypotenuse. And again, this is not new, which is great. Like, again, I get that that idea is new, but once you draw your picture, the good part of this is you don't have to learn a new thing. We're just doing SOHCAHTOA stuff. So how do I get x by itself? How do I get rid of that division of 2?
Times 2 both sides would be 2 cosine 30.
Perfect. So we're going to multiply the 2 over to this side. That way they go away. So your x value is going to be whatever that multiplies out to. I don't know. So 2 cosine 30. Call that 1.7. So there's our x. And then we'll write it as a coordinate here at the end. Our y value is not using x this time, but where y is going to use these two. So which trig function has opposite and hypotenuse in it? Which of these has opposite and hypotenuse? Which one? Sine, cosine, or tangent?
Tangent? Wait.
Tangent has opposite and adjacent.
Oh, so it'll be sin.
Yep.
Well, sine.
Sine. People say it all the time. So sine of 30 is going to be opposite over hypotenuse. So opposite is y. Hypotenuse is 2. And so the solving is exactly the same as this one. We have this division of 2 to get rid of. So we multiply by 2 and multiply by 2. 2's go away. And then our y value is going to equal whatever that turns out to be. So we got 2 sine of 30. Okay, so our coordinate is we will go out 1.7 and up 1. So you definitely went out, and that's 2. So we weren't quite all the way to 2. So that out 1.7 feels pretty decent. And then we were up 1, maybe. I mean, my picture isn't perfect by any means, but potentially. So it actually kind of feels, even compared to my picture, like decent. All right, so if you drew a circle with a radius of 2 and then you went up 30 degrees, you would be out 1.7 and up 1 is kind of the similar coordinate. Okay. So really this polar coordinate stuff really is practicing your SOHCAHTOA stuff and Pythagorean theorem every once in a while. Is really kind of the idea. So same thing on this. This one though is a radian version. So what is pi over 2? How many degrees is that? Because I'd rather think of it in degrees, might be easier. So if we forget, totally fine. Let's kind of refresh our memory here for a second. 2 pi is all the way around a circle, which is 360. Pi is half of that. 180 degrees. So then if we cut that in half again, which is this, we're cutting that in half again. So we're really looking at 90 degrees. Okay. So I want to draw a circle with a radius of 7. See how this goes. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Here's my football circle. All right. And we are, so that's how far out we are because of the 7. And then we are up 90 degrees. So here's the beautiful thing about a picture. You have everything you need for that coordinate. It's not floating out here somewhere where you have to actually figure out the x and the y. What is your coordinate if you're just sitting on the y-axis? It's what, comma, what? What is that coordinate? Right, like how far left and right are you? How far up and down are you?
I have no idea.
0, 7. Right? Your x value, you're not left or right, and you're just up 7. So basically, you are on this, you're just up 1, 2, 3, 4, 5, 6, 7. You're just sitting right there. So your y-intercept is really what you're doing. And so your coordinate then is just 0, 7. So if it lands on an axis, it's not meant to be tricky. It seems like it should be, but it's not at all. Okay. All right. So that's why I recommend drawing stuff, because it might be a lot more straightforward than you realize. And then sometimes it's not. Sometimes when you go out a certain number of degrees, you are floating here. So that's okay. Let's draw a triangle and we'll figure out what our horizontal value is and what our vertical value is. And those horizontal and verticals are your x and your y. Okay. So last little bit to this, I believe, is one last way of talking about vectors is adding them together or multiplying them, or kind of some of the other math that we can do with them. So it says if you're going to add two vectors with the direction of 35, now that's the key. If they're heading in the exact same direction and you put a vector on top of a vector, all it does is just extends the vector out further. So for example, it says if you're adding two vectors with the same direction, that's the key. Okay. And one of them has a length of 4, because remember, a magnitude is really just a length, and the other has a length of 5. Visually, what you have going on is you're taking something that has a direction of 35 degrees with a length of 4, and you're tacking on another piece that's going in the exact same direction, just a little bit longer. So that's also 35 heading in the same thing. We're just going to tack it onto the end. So now all of a sudden, instead of your magnitude being a 4 and a 5, now together your magnitude is 9. All right, as long as they're heading in the same direction, the magnitudes just add together. And so your direction is still the same direction. You're just out further. So your direction is still 35 degrees. Okay, so as long as the direction is the same, The direction stays the same, still going in the same direction. You just are tacking on more magnitude, more velocity, whatever the situation is. Okay, so not meant to be tricky. So again, I think the visual kind of helps if you're heading in the exact same direction. Your other situation is, what if you have two vectors? Now, these things. Now, this 240, we really haven't talked about what 240 degrees looks like. Okay, we haven't really gone past about 90 degrees. So here's kind of the visual of what you have going on. You have a vector going 60 degrees with a magnitude of 6. So let me draw that one. So a vector of 60 degrees going out 6. Okay, you have another vector that's going 240 degrees. Not quite as fast or as far, but 240 degrees. So we got to figure out where we're at. So this is 180 degrees. And if we're going 240, we are going exactly 60 degrees more than that, which is actually very important. We're heading 60 degrees more than that, but it's a shorter magnitude. But the key is that 240 is all the way around, but the key is how many degrees past your x-axis. If that matches that, then they're just, one is heading in the exact opposite direction, which just means it subtracts from the other one. So if you put them together, you have one going in this direction and one going in this direction, exactly the opposite. So if this one is 6 and this one is 4, this one beats this one because there's more magnitude, more velocity to it. But this one heading in the opposite direction just slowed it down. Okay, so all we're going to do is we're going to take the larger magnitude minus the smaller magnitude because it's countering it. So 6 minus 4. So our new magnitude is 2. And we keep the direction of which one won. This one beat this one because there was more magnitude heading in that direction. So the direction is still 60. Okay, if this one was bigger, then our direction would be 240 because it could be swung this way. So then we would still have more heading in that direction. Okay.
What if they're equal in magnitude, or do we need to worry about that?
If they were equal, they would totally counter each other. So you wouldn't have any magnitude and you really wouldn't have any direction. I don't think you'll come across that, to be honest. But if it does happen, literally your magnitude would be 0 and you wouldn't have a direction because you don't have a vector going anywhere. So then you'd have a 0 and a 0. Okay. So they totally negate each other. Okay. One last little bit. And again, this is kind of mainly for people that are heading into the physics class, which may be a couple of you. So it's not totally brand new. There's one last way, of course, to write a vector. Why do we need to write another way of doing it? But unfortunately there is. And it looks like this. Okay, now it's actually far simpler than, like, what the heck? Why is there another new thing to do this? This is actually imaginaries. If you remember back in a math class that if you ever square rooted a negative, you got imaginaries out of it. And this is, how do you graph that? This is actually graphing imaginaries. It's a totally different kind of a grid, basically. Well, it's something you've already done, but basically this 5 plus 3i, 5 plus 3i, the way that you can think of this is it's really just 5, 3 is really the equivalent version of it. And then the 7 plus 2i is really 7, 2. Okay, so when we plot it, and we're plotting this 5 plus 3i, draw that over here. We're going to create a vector out of it, but I'm going to treat it like this. So I'm going to be going out 5 and up 3, and that is my vector for it. All right, and then same thing here. We will go out 7, up 2. Okay, so what they're going to have you do, and the part of why you write it like this is because the next bit of math that we're about to do is going to be a little bit easier to do if we kind of write it in this format. We're going to find this thing called a resultant vector, which is actually what we just did here. This resultant vector is us combining vectors together. We just didn't call it a resultant vector, but that's really what it is us combining it together and creating this new vector. So a resultant vector is literally us just adding them together. Okay. So if you were to take this vector and add this vector to it, especially when you don't write it as a coordinate. When you write it as a coordinate, it's like, what do I do to add this coordinate with this coordinate? If you write it as an equation, kind of like this, it's a little more straightforward of how do you deal with this. So if you take that and you add this, what might you just naturally do?
You'll combine the like terms. So you
Right?
wouldn't you do 3i plus 2i,
Yeah,
and then you'll do 5 and 7.
that's exactly. So you do 12 for the 5 and the 7, and then the 3i and the 2i. That's exactly what it is. So your resultant vector is, when you write it as an equation, it just feels way more natural to just combine your like terms, put the 5 and the 7 together, the 3i and the 2i together. Could you also have potentially thought of that with coordinates? Maybe. It just doesn't feel as natural as when you write it as an equation. But really, your x's are going together to make the 12, and your y's are going together to make the 5. Okay, so that's your resultant vector in complex notation. The word complex means you're going to have i's in it. Okay, so that is your resultant vector. And then if they want to know the magnitude and the direction of it, nothing has changed. We just need to go out 12 and up 5. And we'll draw a picture. So we need the magnitude, which we could call R, we could call hypotenuse, we could call whatever you want to call it. But that's your magnitude. And then we need our angle. So distance out is 12, distance up is 5. And then same math as before. Let's say we do the angle first. Now we'll do the magnitude first. So if we do the magnitude, you got a 5 and 12. How do you figure out the R value? What can we use?
Is it going to be tangent again?
Tangent would be if you're finding the angle. So we'll get to that on the second one. That'll give
Oh,
it
it'd be Pythagoreans, right?
Yeah, Pythagorean to figure out the magnitude. The magnitude is this piece. So we'll do both. So we'll do the magnitude first. So we got 5 squared plus 12 squared is going to equal the radius squared. So it's 25 plus 144 equals r squared. So that is 169. Square root of that. Oops. Is 13. So our magnitude is 13. All right. And then if we wanted to figure out the angle, we would be using tangent because we have opposite and we have adjacent. So we're looking at TOA. So tangent of our angle that we don't know would be 5 over 12. So since we're finding an angle, that's the only time we'll use that inverse. And I have no idea. Let the calculator figure that out. 22.6. And that is our direction. Good. And if they ask for polar coordinates, that's your radius and that's your angle. Okay. So it all kind of connects together. It's the same process every single time. They're just asking different ways of doing it, or not different ways, different questions, all related to the same process. Okay. That good? Okay. Decent? Maybe? All right. So one last little bit before we get on to solving triangles that are not right triangles. Okay. We're going to find the resultant vector. So same thing. A vector that has a magnitude of 2.8 and a direction of 45 and is multiplied by a scalar of 3. All that means is it's going to triple it. So visually, what you got going on is you have something that is heading in a direction of 45. And its magnitude is 2.8. What do you think happens when you multiply it by a scalar, which is just the language that they use for it, that has a magnitude of 3? So the word multiply. What do you think that gets multiplied? Do you think it changes the direction? Do you think it changes the magnitude? Or do you think it changes both? What do you think? My hint is it won't change both. So do you think it changes your direction, or do you think if you change your magnitude, your distance out?
Change the magnitude
Exactly. By how much?
by a factor of.
Yeah, you just triple it. That's it. So basically it's like having 3 of these. You just do another one, you do another one. So that's all that changes. Your direction is still your direction. By you multiplying it by something that has a magnitude of 3, doesn't change a thing. You're still heading in the exact same direction. So magnitude was 2.8, but it's being tripled. So now, whatever 2.8 times 3 is, I think it is now 8.4. But direction does not change. No change. Okay. So this scalar thing only ever affects the length of your magnitude. That's all it ever does. It'll never change the direction that it's going. Okay, so whatever it is, you're going to take that value and multiply it by whatever the original magnitude was. Okay, so hopefully not too crazy. Again, we're trying to build off of stuff that we already know, so I know that they have formulas and things like that, but it's still just SOHCAHTOA and it's still just Pythagorean theorem. Depends on how they give you the original stuff. Do they give you as circles and then angles, or do they give you as a coordinate and then you want to find angles and radius and stuff like that? So it's kind of just a forwards and backwards process with it. Okay. So that finishes the right triangle stuff. The last two sections, 20.4 and 20.5, is your non-right triangle. And there's two ways to solve it, and you have to figure out each problem is going to potentially use one method or another. You can't use both on every single time. It's kind of dependent upon what you're given. One is called law of sines, and the other one that we'll do is called law of cosines. The law of cosines we'll do next time. Law of sines has a tendency to be the most straightforward one, because here's what it looks like. Law of sines is just proportions. Now, they give you more information than you need. Typically, we're going to use basically a proportion. We're going to set up a proportion and we're going to cross multiply. Okay, so it could be this combination, it could be that combination, it could be that combination. You're going to use 2 out of the 3 fractions. Okay, you'll never use 3. All right, so it's all dependent upon what you have. It depends upon the situation. So this has a tendency to be, this is probably the method that you'll use more often. If you can, this is probably the preferred method because it's a little more straightforward. However, because of course it's the easier of the two, there's got to be a hitch to it, and there is. And so we'll talk about that on the next page. But let's kind of walk through one and let's show how do we use this. So law of sines and law of cosines is for triangles that are not right triangles. SOHCAHTOA does not work unless you have a right triangle, and we don't know. Okay, and to be honest, they're not going to be right triangles. Okay, so you can't use SOHCAHTOA and you can't use Pythagorean theorem because they're not right triangles. Those only work on right triangles. So for law of sines, how do you know when you can use law of sines versus how do you know when you have to use law of cosines? I always start with, can I use law of sines? And if I can't, then I use law of cosines. It's a process of elimination. Okay, but how do you know when you can solve with law of sines? Well, think about how you solve a proportion. So with a proportion, if you just set up any natural proportion that you're going to cross multiply with, 2 over 3 equals 5 over whatever. Okay, that's a basic proportion. So once you see that, that's a cross multiplying kind of a thing. But here's what we need to get out of this is you have to recognize that you know 2 or you know 3 out of the 4 pieces. This is the only one that we're missing. And not only do you know 3 out of the 4, you know 1 full fraction. That's the key. Must have 1 full fraction. If you can create 1 full fraction, you can use law of sines. Okay, so over here it says, how do you know when you use law of sines? It is, do you have 1 full fraction? That's the key. Okay, so what you're looking for is you need to know an angle and a side across from each other, right? You need to know angle A and side A. If you know those 2 values, guarantee you can use law of sines. If you know angle B and side B, guarantee you can use law of sines. If you know those 2, guarantee, okay? So you need to have a side and opposite angle. Okay, they have to be across from each other. If you know that, you're good to go. Okay, and then basically the process after that is once you set it up, you're going to cross multiply. You're going to cross multiply and solve. That's it. Okay. So biggest thing is you're going to be given information, but probably no picture. So you got to draw a picture. Okay. When we get to the one that's an issue, there is a situation that law of sines kind of can be a little more challenging. We'll have to draw our picture a very, very specific way to help our cause. But right now, we're just going to draw a picture. And this is not going to be drawn to scale. I'm not even going to pretend to try to draw it to scale. I don't care. I'm going to try and draw it probably like that every single time. I don't care. I'm not going to try to make this perfect because it doesn't really matter. So I'm just going to draw a triangle. We'll say that's A, we'll say that's B, and we'll say that's angle C. Okay, so across from, remember that across from angle A is side A, which we don't know. We know angle A is 50. We know angle B is 75. And we know side B is 12. That right there tells us that we can use law of sines. As soon as I know an angle and a side across from each other, I guarantee I can use law of sines. Okay, so how do we use law of sines? So we're missing side A and we are missing side C and we are missing angle C. So it says solve the triangle. That means find those missing pieces. Okay. Is there anything we can do right away that does not involve any of this?
Subtract 75 and 50. Subtract 75 and 50 from 180.
Cool. So we can get angle C. Now you don't have to start with that, but if you see it, might as well get it done. It's probably the easiest of all of the stuff we're about to do. So why not start with that? So angle C is going to be 180 minus the other two angles. Now, not every situation is going to start like that, but if it does, why not take advantage of it? All right, so we're going to take 180 minus 75 minus 50. So 55 degrees. Great. All right, so I'm going to start to kind of input some stuff here. That things that I find, I'm going to put in parentheses. Because in the end of this, there is a way for me to quickly spot check, does this feel right? I mean, it doesn't guarantee that I'm right, but probably I headed it in the right direction, which is good. I also want to adjust this. I don't know why. I always write it the other way around. I always put the angles on top, and I don't know if that's just how I first learned it. It's so weird for me to go the other way on it. So I'm just flipping it. I use that one. It literally doesn't matter. As long as the angles stay all on the bottom and all the sides on the top, or all the angles on the top and all the sides on the bottom, literally doesn't matter. I don't know why. I must have learned it that way, and change is hard. So stuck in my ways. Okay, so again, back to that first question. Can I use law of sines? Because if I can't, I would have to shift to law of cosines, which clearly we're not on that section. So we obviously have to be able to use law of sines on this. And this is the key right there. Can I create one full fraction? Yes, I can do sine of 75 over 12. That's one full fraction. Beautiful. Now I'm going to go to the angle that we already knew, and then I'll finish with the angle that we found out. Okay, I'll do that last. But 50 is angle A, and it's across from side A. So I can set this equal to sine of 50 over A. So that's me creating a proportion. So sine of 75 over 12 is going to be equal to sine of 50 over a. And then, like I'm sure you've seen in multiple kinds of classes, we cross multiply to solve. So I'll take my variable cross product here. So I'll do a times sine of 75, and it's going to equal 12 times sine of 50. And I got to get a by itself. So this is multiplied to a. So I undo it by dividing it. Right, so that goes away. So a is just going to equal whatever that turns out to be from the calculator. I have no idea. Now, let me show you if you have this calculator. I guess it really doesn't matter. I can do 12 times sine of 50. Please make sure you close your parenthesis there. And then divided by sine of 75. Like I don't have to make a fraction because it's I'm only dividing by one thing. And so I should be totally good to go. So 9.5. So A is 9.5. So let me add that to my picture. All right. And then piece that I'm missing would be C. So I'm going to go back to my full fraction again. It's almost like a scale factor from back in the day. And then I'm going to do sine of 55. And this time it's going to be over C. Okay, so really the only thing that changed was I had 50 that went with this angle, right, because they're across from each other. Now I'm doing a different setup, different proportion, but then it's these two. Okay, so kind of these corresponding pieces need to go together. And then same stuff, cross multiply. So it's C times sine 75 equals 12 times sine of 55 divided by sine of 75. I have no idea. Calculator on that. So 12 sine 55 divided by sine 75. 10.2. Okay. So here's how quick my spot check is after I have my answers. So the ones in parentheses are the ones that I figured out. And I don't know 100% if I'm right, but there's something that should happen right now that kind of things have to line up correctly in order for me to be like, yeah, I'm probably okay. Assuming that I did the right numbers here, like I didn't accidentally not put 55 and I put 65 or something like that. But basically my quick spot check is my largest angle should be across from my largest side. So 12 is the largest side. And then my smallest angle should be across from the smallest side, which lines up. And then my middle angle should be across from the middle side. Most likely I'm okay. Again, as long as I didn't screw up the numbers, like my setup was good. As long as the numbers, I didn't botch the numbers, kind of putting things into the calculator. As long as that happens, I'm probably okay. All right. That's kind of my quick, like, yeah, I think that feels okay. It's not a guarantee by any means that I'm right, but if something went wrong and all of a sudden this ended up being the shortest side, but it's not supposed to be, then I'm like, okay, something went wrong. What did I do wrong? Okay, so just kind of a quick spot check to it. All right, how's law of sines? Proportions, basically, setting up cross multiplying. Decent?
So far, okay.
So far, okay. Decent, maybe, hopefully. Okay, so let's do one more. Make sure we're good. And then we'll give you the bad news. All right, so another one. Again, I'm going to draw a picture. I'm not even going to come close to trying to draw it to scale. I don't care. I just need to draw my picture. So I have an angle, and a side. So you'll see my pictures pretty much look the same every time. Don't care. So call that A, B, and C. So this is 35 degrees. This is 40 degrees. And side A over here is 7. Okay. So what I'm missing is side B and side C and angle C. So we could do the exact same thing that we started with on this one. Is we knew 2 of the 3 angles, so right away we can jump into finding the angle measurement again. So why not? So C is going to equal 180 minus the 35 minus the 40. I don't know. So 180 minus 35 minus 40, 105. Okay, so angle C, 105. Okay, so side C should be the biggest side when we get all this done. And then A should be the smallest because of the angle. So B should be bigger than 7, and then C should be bigger than B. Okay, that's kind of a quick spot check. Are we heading in a good direction? All right, so do we have one full fraction? Do we have one full fraction?
Yes.
We have that one full fraction means do we have an angle and a side across from each other? Which if we have that, then we can create one full fraction. Okay, so that's what we're looking for when I mean that. Okay, one full fraction is angle side. So we can do sine of 35 over 7. Okay, and then we can just pick whatever. So let's say we do C, since we know that that's supposed to be the largest. So we'll do sine of C, which is 105 over little c, because we don't know what it is. So cross multiply. So C times sine of 35 equals 7 times sine of 105. And then we'll divide by the sine of 35 over. Divide that over to cross it off. So C is going to equal whatever that turns out to be. So 7 sine 105 divided by sine 35. Okay. 11.8. Okay. So that's supposed to be our biggest side. And B should be somewhere in between 7 and 8.5. I'm guessing since this angle is close to this angle, it's probably going to be closer to 7. I have no idea how close it's going to be, but it should be closer to 7. So we'll set this up as we'll go back to our same full fraction that we had. So these two across from each other, there's our one full fraction. And then we'll set it equal to, we don't know that one, so sine of 40 over B. And we cross multiply. So we cross multiply, we got B times sine of 35. So that's that cross product equaling this cross product. 7 times sine of 40. We'll divide the sine of 35 over. And then whatever that is should be somewhere between 7 and 11.8. So 7 sine 40 divided by sine 35. 7.8, somewhere in between 7 and 11. That's good. So, good. So that value is somewhere between these two values, and it was favoring the 7 just because the angles were decently close to each other. So that all feels okay. All right, so that's what we got for law of sines, kinda. There is a hitch, unfortunately, that there is a situation that, depending upon what you're originally given, and so here's what you need to be given. It says when you have two sides of a triangle and the angle opposite one of the sides. What that looks like means side, side, angle. Okay, and we'll show you what that is in a second. Is if you have a side, side, and an angle, and that angle is going to be across from, so that angle and that side at the front here, those two are across from each other. So if you have that one full fraction with one more side, then there's potential that you could have two triangles. So bad news is if you have two triangles, you're definitely going to have some more work involved. And there's a process to it. And so we're going to do an example that kind of involves this. And here's what happens. So here's kind of this picture. And I draw my picture very, very specific every single time. Because one of the sides, and here would be, this is what you would be given. You would be given that angle, the side across from it, and one more side. Okay, those would be the pieces that you would know. You would not know that angle. You would not know that side. Okay, but unfortunately, this is like a Goldilocks thing. That side, when you compare it to this side over here, it's like there's a certain size that it's Goldilocks. There's just the right size that if it's just the right size, it could be in this location or it could rotate over to this location, creating this triangle or creating the bigger triangle. So that's the bad news. So we got to figure out the Goldilocks. We want to figure out, is this B in this certain range, not too hot, not too cold kind of a thing. And if it is, then we're going to have two triangles. We're going to have to figure it out. Okay, so the first part of this is this piece has to be smaller than this one. That's a must. Okay, if it's bigger, like this picture, then when you try to swing it, it swings way over on the outside of the picture. Okay, so so right away, this thing has to be smaller than this. But it also is going to compare to the height. So if we were to drop this piece down, it's got to be bigger than the height, but smaller than A. That's the Goldilocks. That's what we'll have to figure out. Okay, so we're going to do one. And there's definitely some work to it. But the good thing is that we're going to keep on using this method. We're going to be using law of sines over and over and over again. We'll have to do it a total of 3 times. So even though we're going to draw 2 triangles, we're only going to add 1 more law of sines to figure out the second triangle. Okay, so it's not a crazy amount of additional work, but it's definitely additional work. Okay, so the first part of this is, do we have the Goldilocks thing? Do we have this side here that's just right? So this is Goldilocks. Goldilocks, I don't even know how to spell it. So we're going to check for just right. Okay. Read the story to my daughter and I know how to spell. All right, so here's what we got. Now I will tell you that this is going to be the just right situation. So I have to cram the space here. It's very limited, unfortunately. So yeah, I'll do my best. So I need to plan this better next time. I need to give this more space because we need it. So first thing is that Here's that side, that angle in the side across from it with an additional side. Okay, that's the potential Goldilocks that we got to figure out. Okay, this side is a side-side angle. So there's potential. Don't know for sure. Okay, so I'm going to draw this triangle a very, very specific way every single time. So I'm going to draw it like this. I'm not worried about my letters so far yet. But what I'm going to do is I'm going to purposely not connect that side. This is my Goldilocks side. This is the side that could swing and create two triangles. So I want it to stand out, okay? Which that means that this is the angle and the side across from it. Okay, so that's an 8. Okay, so I don't care about the letters or anything. I just know that the side and the angle across from each other, those are the two that are going to kind of play this role here. All right, and this is the piece that could swing and create another triangle. Now I'm going to tell you right now on this one, it is going to. Okay, so I'm going to show you how do we figure that out. First thing is I'm also going to label my other piece, whatever number it is or whatever letter it is. I don't know why all of a sudden that thing becomes 3 decimals. But this is the one that we got to figure out the magic on, the Goldilocks, okay? What I need to compare this to is the height. Sorry, what I need to compare this to. I want to see if this is in between this one and the height. Okay, so my height here's how I find it. I basically have a right triangle right here, and I want to find that height. So this is just a little extra piece that I have to find that doesn't have anything to do with my final triangle. I just need to basically see if 8 is in between these two values. That's the Goldilocks. That's the just right, not too cold, not too hot, hot, cold, whichever one you want. Is 8 right in between these two? If it is, we have 2 triangles. Okay. So to figure this out, the nice thing is that I can ignore the fact that I don't have a right triangle for a second, just for a second. And I can do sine of 25 is going to equal the opposite over the hypotenuse. H over 11.426. Okay. Now to figure out what H is, I could multiply the 11.426 to the other side. So my height's going to be 11.426 times sine of 25. And that's just something I throw into the calculator. Sine 11.426 sine 25. So 4.8. Okay, Goldilocks is happening. 8 is between 11.426 and 4.8. So we have 2 triangles. Okay. So I'm going to solve the first triangle. I don't care about the second one yet. I need the first to help me solve the second. Okay, so right now, business as usual, let's go about solving it. Okay, so first triangle. And this is where my micro print's got to happen. If you are using this, I would maybe draw all that on the back or something. I don't know, because you're going to need some space. So let me start over. Let me draw what I have. So this is 25. This is 8. This is 11.426, which was B, which puts my big B over here. And then my big C is going to have to be there. And I don't know that. Okay, so business as usual, right? We're gonna solve like normal. So here's my one full fraction. So I have sine of 25 over 8, okay, is going to equal, these are the other two that I know one of the two pieces of, but I don't know the angle. So it's going to be sine of b over 11.426. And we cross multiply. So that process, nothing's going to change. We are going to have to do the inverse sine here to figure out the angle, but we'll get to that. So we'll do our cross multiplying. I like to do the variable one first. So we have 8 sine of b equals 11.426 sine of 25. And then I'd have to divide by 8. So sine of b is going to be whatever that decimal is. I have no idea. So 11.426 sine of 25, make sure you close parentheses, divided by 8. Now, I want to keep this as exact as possible. So I want to use all the decimals. I just don't want to write all the decimal. So I'm just going to take the first two, not round, not do anything. So I'm going to just, I don't want to keep writing all these values. So I just put a ... in there. So I know I haven't rounded it. I'm going to use everything. And then I'm going to be doing, to finish this off, angle B is going to be the inverse sine of that decimal. ... Okay, so this tells me that I'm not rounding, I'm not doing anything. I just want to rewrite it. So I'm going to do inverse sine. And remember, it depends on the age of your calculator. If you have somewhat newer one, I mean, this is old, but you might be able to just highlight that and do that. Or you have to inverse sine and then do right above the negative says answer. It's going to take that last answer and populate it in there for you. It doesn't write it out, but it is using the last answer. Okay, so that's your angle measurement. So 37.1 degrees. Okay. So angle B is 37.1 degrees. Okay, so 37.1. All right, we do have two angles. So I'm going to find the third angle here. So I'm going to separate this out. So angle C is going to be 180 minus 25 minus 37.1. Don't know. 180 minus 25 minus 37.1. So 117.9 for that top angle. All right, so we have our two angles. The only thing left, so that's 117.9. The only thing left is to find side C. So I got to do law sines one more time. So this is totally normal from what we were doing on the last ones. So not, lost my page. But it's still the same amount of work, regardless right now of whether we have one triangle or two triangles. So this is still totally normal. We're just going to do one last piece. We'll go back to our original. Sine of 25 over 8. Now we'll do these two pieces. So sine of 117.9 over little c. Cross multiply. So we got c times sine of 25 equals 8 sine of 100 and print here, 17.9. Divide by sine of 25. Cancel that. So little c equals. So I need 8 sine 117.9 divided by sine 25. 16.7. So that's how long c is. Okay, so quick spot check. Biggest angle, biggest side, yes. Smallest angle, smallest side, yes. Okay, so that part feels okay. Now we're going to have one last law of sines we have to do the second triangle. So here's where we kind of go back to this. So I'm going to draw two triangles. So I'm going to kind of draw it up here at the top. That this thing right here swings and creates a smaller version of this. Okay, so here's what we got going on. So this is my second triangle. And by far the most work was all right here. There's a little bit of work to kind of finish this off. So what we have going on is this was 25, this was 8, and this was 11.426. Okay, but this piece is just the right size that it could swing to here and make a second triangle. Okay, so our new triangle that we're about to solve is still 25, but its 8 is on the inside as opposed to kind of on the outside. That's the difference. But you could still have a 25-degree angle. You could still have this 11.426. It's just 8's over here rather than over here. It's just the right size that it could be in either location. Okay, so this is still A, this is still B, this is still C. So we're missing little c. We're missing angle C, we're missing angle B. So it feels like we're missing a lot of information. But this picture is about to help us. Okay, this angle right here that we found is going to play a pretty significant role. That if this thing is 37.1, now if I just look at this triangle, this kind of multiple, kind of the swing here, this thing is also 8, making an isosceles triangle. And if this angle is 37.1, that means this angle is 37.1, which now these two make 180. So this angle right here is 180 minus the 37.1, which is 142.9. 142.9. And that is this obtuse angle right there, which is this angle right here, 142.9. So for our second triangle, we already have angle B, 142.9. Okay, and that's always, always, always the thing. That angle in your original triangle is the same as this angle over here, which helps you get this bigger angle, this obtuse angle here. And it's always by taking 180 minus that angle, which is always the same as that angle. That's how it starts to get your second triangle. Now, the good news is now we know 2 out of the 3. So angle C is going to be 180 minus 25 minus 142.9. minus 25 minus 142.9. 12.1. So there's angle C. Okay, and then I did say we had to do one last law of sines. It's because we know that this angle is 12.1, and that's the piece we're missing. So we go back to the beginning. Sine of 25 over 8 equals sine of 12.1 over low c. One last solving. All right, so cross multiply, we got c sine of 25 equals 8 sine of 12.1. Okay, so we have that cross product equaling that cross product, divide by sine of 25. So c is going to equal whatever that turns out to be. So 8 sine 12.1 divided by sine 25. So we'll call that 4. Okay. 0. So biggest angle now, biggest side, smallest angle, smallest side. So those values are all right here are the second triangle. These values are all the first triangle. And that is as ugly as it gets, which is ugly. But it all stems from this Goldilocks thing. Is do you have two values across from each other with an additional side? If you do, you have to compare that side to these two. And it's got to be just right. Is that value in between these two? And if it is, this world exists. If it's not, then totally normal. One triangle, business as usual. Okay. So I think we got enough time to finish one last version, and then come Wednesday, we'll finish this one. I don't think we'll have enough time to finish that one. Okay. All right. So I know we're gonna probably have questions, but we can come back and talk about that one again on Wednesday for sure. We can walk through the process of it. Okay. So let me at least get through one more, and then we can answer some questions on Wednesday before we run out of time. All right, so very first thing is I have these two pieces across from each other and an additional side. So that means there's potential for a side-side angle situation here. Okay, there's potential. So I draw my picture anticipating that this is going to happen. Okay, I purposely don't connect because that's my one that can swing. So that's my angle C. My side across from it is 12. And then this is 10, which locks this at angle B. Okay, so I draw it the same thing every time because once I start turning it, and I don't know which side swings, my mind just can't connect what's going on anymore. So I have to lock it a certain direction every single time. So there's potential that this thing can swing, but it's the Goldilocks. 12 is bigger than 10. The Goldilocks is not happening. Remember that that piece needs to be in between these two values. And it's not going to be. So 12 is greater than 10. Only one triangle. That's good. So we won't have the extra, but we still will have this work. Okay, that's totally normal. All right, so it's still gonna be work, just not as much. So I'm gonna connect this because there isn't that possibility of swinging anymore. This is it, we just go right through it. So sine of 40 over 12 And normally we try to find our angle, but I don't have 2 out of the 3. I will have an angle once I find B here, and then we can do that, but I don't have 2 out of the 3 angles, so I can't just do the 180 minus the angles. So I actually have to do law of sines right away. So sine of 40 over 12 is going to equal sine of B over 10. We'll cross multiply. So again, I do the variable one first. So 12 sine of B equals 10 sine of 40. We'll divide by 12, divide by 12. Sine of B is going to be, I don't know, something. 10 sine 40 divided by 12. 0.53 and then a bunch of decimals. 53 and a bunch of stuff. I have to do the inverse sine to figure out the angle. Okay. So inverse sine of that gives me 32.4. All right, there's one. All right, now, there's angle A. We could figure out angle A. So A is going to equal 180 minus 40 minus 32.4. So 180 minus 40 minus 32.4. 107.6. So there's my largest angle. 107.6. So my largest angle is there. So my largest side should be A when we figure that out. So I go back to my original full fraction that I know equals sine of 107.6 over little a. Cross multiply. So we got A sine of 40 equals 12. Sine of 107.6 divide by sine of 40. A is, I don't know, but it should be my biggest side. 12 sine 107.6 divided by sine 40. So 17.8. Okay, so quick spot check is definitely the biggest side, biggest angle, smallest side. Cool. Feels okay. All right, so we got one last that's going to involve law of sines. I can tell right away because it has these two values. And you do have actually this exact situation, but that one is bigger than that one. So basically it's going to look just like this again. You don't have the two separate triangles. But we're running out of time, so we'll do that next time. All right, so we have one more problem. We have probably 30 to 40 minutes of new stuff, maybe 45 kind of with the law of cosines. And then I will talk about kind of the final, what we got to finish. I'll show you on D2L, I'll add the link on there for the evaluation. And then I'll show you that I'll have an Excel file to kind of, what do I need to get to kind of see where you're sitting basically, where you can kind of play with the numbers and see what you need to get on your final to kind of get whatever grade you're looking to get. And I'll show you the spot for the evaluation so you can take a screenshot and shove it in there. I'll make sure that's all set up for next class. Okay, so